Because why? Why is that the case? Well, because as we saw, most of the patterns that we try to mine or try to learn from our data are based on distance computations. Yeah, we compare distances and say, okay, this is more similar to the other one, have a smaller distance to the other one. So this is, for example, still in the same cluster, and the distance from here to here is larger. So there is these two objects are in different clusters. Yeah, so that is a bad result, obviously, a bad story, a bad message. Yeah? And one of the consequences of this concentration distance of distances is the next point that we get. This way, which is that the concept of neighborhood becomes meaningless. So, well, there's maybe something which is quite obvious or quite intuitive. So if we have problems with distances, all pairwise distances become more or less the same, have the same value, then what is my nearest neighbor? Virtually anything is my nearest neighbor. All the other points have more or less the same distance to me. Yeah? So what is my nearest neighbor and what is my farthest neighbor? You cannot say anything about it anymore. It's not really meaningful anymore. Yeah? So that's the implication from the concentration. A lot of data mining methods, of course, use distances and neighborhood concepts to define patterns. Yeah? K-nearest neighbor classifier, density-based clustering, distance-based outlier detection, but of course also all these model-based things. A Gaussian distribution somehow models the distance to the expected value, yeah, to the mean value in some way. So also a Gaussian distribution relies somehow on the concept of distances, yeah, and that distances are different actually. Yeah, and with neighborhoods. Using neighborhoods is based, of course, on a key assumption. Objects that are similar to an object, O, are in the neighborhood of O, and objects that are dissimilar, have a high distance to O, are not in its neighborhood. Yeah? But once again, if all the distance values from O to all the other objects are more or less the same, if O has more or less the same distance to all the other objects, what is the neighborhood of O? Yeah? So what if all objects are in the same neighborhood? Yeah? So anyway, neighborhoods, or the concept of neighborhoods become somehow meaningless, and we can even further formalize this here with the definition of so-called unstable neighborhoods. So a query, a nearest neighbor query, is called unstable for a given error term epsilon. In the following case, well, we look at the distance to the, so let's say here Q is the query point, and we look for the nearest neighbor of Q, which is this one here. So this is the nearest neighbor distance here, this one here. D min is the nearest neighbor distance of Q. And given this error term epsilon, we say that the nearest neighbor query is unstable if within the radius of 1 plus epsilon times the nearest neighbor distance, yeah, we find most of the other points. Yeah? So if the distance from the query point to most of the other points is less than 1 plus epsilon times the distance from the query point to the nearest neighbor. So that means that most of the query points, most of the other points are in between this solid line circle and the dashed line circle. Yeah? So if all the other points would be within this circle here, the nearest neighbor query around Q would be unstable. So in that case, it's obviously not the case, yeah, because most of the other points are not here in this kind of cylinder or whatever. So in this case, it's not unstable. Yeah? But it would be unstable if more or less every other point would be in more or less the same distance range of the nearest neighbor. Yeah? And it can be shown, we don't do that here, but it can be shown that with growing dimensionality, the probability that a query is unstable actually converges to 1, to 100%. And here is an example of such an unstable nearest neighbor. So that would be the query point here, this X here. So, and all the other points are actually on a circle which is centered here at this point, which is very close to the query point. Yeah? So the nearest neighbor would be probably this one here, and you see that all the other points are more or less have more or less the same distance to the query point x here as this nearest neighbor here. So in that case, it would be within this solid line and dashed line circle here. Yeah? So if you just draw the same circles around here, depending of course on epsilon, yeah. But again here for a very small epsilon, even the whole thing just converges to 100% if the dimensionality grows. Yeah, that can be formally proven. So unstable neighborhood, and we can even formalize it in yet another way, so to say. Yeah, in that case, we consider d-dimensional query point Q and n d-dimensional sample points independently and identically distributed, and then we define two dimensions here, which or distance measures here, or distance constants, so to say, which are already shown here in this figure, also here in this figure. So d min is the distance to the nearest neighbor, and d max is the distance to the farthest neighbor of Q. Yeah, so that is again here. So d min is the x which is closest to Q, the query point, and or the distance to x, the minimum distance of 1x to Q, and d max is the distance to the farthest neighbor, so the maximum distance we get from all the other points in our data set, yeah, to Q. So the theorem actually formalizes exactly this idea of an unstable neighborhood somehow, because it says that if this one holds here, what is this one here? Well, look at this thing here. It's the variance of the distances times the expected values of the distances. Wait a minute, we said that the expected value actually grows, yeah, with the factor of square root d, and the variance of the norm. So we just look at the norm. So we had this this thing here. So the norm actually, the expected value of the norm actually grows with the factor of square root d, while the variance just remains the same. Yeah, or at least yeah, stays constant or diminishes to 0. Yeah, so if this one here actually this quote here actually diminishes to 0, which is actually the case, exactly what we said before. If we increase d, then the variance becomes 0, and this one here becomes something which is less than 0. So we get 0 here actually as the Grenzwert, the limitation here, yeah, as the limit. So if the dimensionality grows, this one actually holds for our assumptions that everything is independent and identically distributed and stuff like that. So if this is the case, which is the case for our assumptions, then we can prove that for any error term here, yeah, the limit or the probability that the distance to the farthest neighbor is smaller or equal than 1 times epsilon, 1 plus epsilon times the distance to the nearest neighbor equals to 1. And that's exactly what we have stated here, that everything, well, d max actually, everything here is basically placed or located within these two radii here. Yeah, so that's actually what happens here. Yeah, so the distance to the farthest neighbor is closer to Q than 1 plus epsilon times the distance to the nearest neighbor. Yeah? And that's exactly what how we defined unstable neighborhoods. Yeah, so so if this holds, yeah, with growing dimensionality, the probability that the neighborhood gets unstable equals 100%, yeah, or becomes 100%. Yeah, so all points actually converge to the same distance from the query. So if I'm a point, a data point, everything else is more or less has more or less the same distance to me. Yeah, that's the point in high dimensional data sets. So once again, something like the nearest neighbor, an epsilon neighborhood, the distance all these things are actually becoming meaningless in high-dimensional cases. Yeah. Not always. Look at the assumptions that we had. Yeah, that the features are independent and identically distributed. We have to say that. Only in that case we have that the variance of the norms are actually zero or become zero with increasing dimensionality, and only then we have the expected values of the norm become something which is actually square root of d. Yeah, so only then in this under these assumptions this precondition actually holds. But then it holds, and then we have unstable, or the probability that we have a lot of unstable neighborhoods is extremely high. Yeah, becomes 100% in infinity.